Welcome back, chemistry fans. Today, what we're going to do is Unit 6, Topic 1. This is all about this new concept called stoichiometry. Stoichiometry is a very fancy word for conversion of units using dimensional analysis. It also means that what we have to understand is a lot of our prior knowledge is going to come into play, like how to predict products, how to balance a reaction, how to convert grams to moles, moles to grams. All of this comes into play in one big problem. And there's going to be two ways that we can solve it. So let's jump into it. There's an easy way, there's a hard way, but we'll figure it out together which way you prefer. Let me share my screen with you and we're going to jump right into it. Now, the spelling on this one is awkward too. Stoichiometry. Good luck with that one whenever you need to, but maybe that should be one of the questions on the test. When we get into this topic, it should look vaguely familiar to you because if we just took one half of this image, what I'm hopeful you would see is that it's a mole map. And then if we just simply double the mole map, maybe we could see a path, the logic behind what we're trying to accomplish here. So let's take a step backwards and remember a couple of units ago, last year, you talked about how to make these conversions. And if you recall, if we want to go moles to grams, we multiply by the weight off the periodic table. If we want to go moles to liters, we would multiply. If we want to go moles to molecules, we would multiply. But if we wanted to go in the opposite direction, if we started with moles and we wanted to, if we started with grams and we wanted to take it into moles, we would divide. If we had atoms, molecules, and we wanted to take it into moles, we would divide. And similarly, if we would have liters and we want to convert it into moles, it would be a division process. So you follow the arrows and it guides you as to what the process is. What you divide by is dependent on these values or these terms that are in between where the arrows are. And so this is how we made some conversions. So all that should be somewhat comfortable with you. Let's make sure, let's do a quick little review of what that means. So if we have 2 moles of water and we want to convert it into grams, we consult our mole map and we are starting with moles and we want to move towards grams. We should multiply. What do we multiply by? The weight off the periodic table. Hydrogens each weigh 1, oxygen weighs 16. You sum all that together and you get 18 grams per mole. So that's where the values in this practice problem come from. Now, the dimensional analysis side of this is that to cancel out a unit, what you would need to do is make certain that the top value as well as the bottom value are the same. And that's how we always make sure that the correct unit is on top. You multiply the values on top, you divide by the values that are on bottom. So multiply all the values on top, divide by the bottom. Well, dividing by 1 doesn't change anything. And you're saying, well, why did you even put the 1 there? Because the unit of those grams are 18 grams of H2O for every 1 mole. The unit is actually 18 grams per mole if you look at it on the periodic table. And so here's your grams, here's your moles. This also allows us the ability to understand how the ratio works in conjunction with a given amount. So it's grams per mole that we would need to multiply by. Now that might confuse some of you. You're just saying, I remember to divide it by 18 or I multiply by 18. Then that's fine. That's fine. That's perfectly comfortable. Just know that this is part of the dimensional analysis that we're going to have to understand moving forward. Because we're not going to have just 1-step problems. We're not going to have just 2-step problems that we've had in the past. We had the capability when we looked at one of these mole maps to go from grams into liters. We could convert by going to moles and then going back out to liters. Well, what if, though, we have a reaction? What if we have 2 different substances? How do we relate one to the other? It's going to be through this mole ratio that we've established with a balanced chemical reaction. So if we know that mole ratio, we then know that if we are in a 2-to-3 ratio, that if we can convert grams into moles, I can then convert moles to moles through this ratio. It's a 2-to-3 ratio. And then I can convert it back out to grams. So it's a very useful tool for chemists in that they can start with a given amount and they can end with a different amount, different substance. We are going to make our path through this double mole map. So, giving definition to stoichiometry. Stoichiometry is this relationship between the amounts of reactants that are used and the amount of products that are formed. So we're trying to establish some mathematical way to convert amounts on the left into amounts on the right, and they are different compounds. So that's going to make it a little bit more challenging. It's not just as straightforward as using the mole map. One of the things we need to remember is that we have these balanced compounds. The number, there are 4 H's on the left. The number of elements on the left must be equal to the number of elements on right. So if you're asked to start with from scratch, given 2 reactants, you're going to have to be able to predict the products. You're also going to have to be able to balance your reaction. Notice that there are 4 oxygens. Here are 2, and here are 2. So that's a total of 4. There's only 1 carbon, 1 carbon. So that's how we balance a chemical reaction. Now, we must also remember that ultimately, these weights must equal. So if I have 1 carbon, well, it would weigh 12. Well, I'm going to have 12 over here. If I have 64 as my weight of oxygens, well, over here I'd have 32 and I'd have 32. Those weights are going to be the same. So overall, the weight on the left side must equal the weight on the right side of this compound. Some terms that are important for us to know moving forward. The large numbers in front, they are representative of the number of moles of that material. If there is no value written there, its mole value is 1. We call those coefficients. But the subscripts, those are actually the number of atoms. So what we're saying is I have 2 moles of 2 atoms of hydrogen, meaning I have a total of 4 atoms. Now, what that means is, remember, a mole is not only a weight, but it could also be the number of total atoms. So if I have 1 molecule of H2, I'd only have 2 atoms. But if I have 2 moles, well, a mole is 6.02 times 10 to the 23rd. So what I'm actually saying, if you can fathom this, is that you have 6.02 times 10 to the 23rd multiplied by 2, multiplied by 2. So you actually have 4 times 6 to the 23rd to figure out how many atoms of hydrogen you would have total. So now that gets a little bit more confusing if we have to think about it in terms of that mole map. That moles are not only a weight, they're also the number of atoms. But these are all things that we will be reminded of as we move forward. I must also reinforce the idea that the reactants are on the left, the products are on the right. So whenever we have these terms, make sure that you're aware of what they mean. Here's that mole ratio again. Now, do not count the number of atoms as moles. So you wouldn't put 4 there. What instead we would say is that this is a molecule and this is a molecule. So we have 2 molecules of H2. We only have 1 molecule of O2, and it's going to produce 2 molecules of water. So the ultimate ratio is that there is a 2, there is 1, and there is 2, and that's what the mole ratio is. Now, we don't have to use all 3 of those values. We could segment this out and say that the mole ratio is a 2-to-2 ratio, or we could talk about the oxygen to water ratio being as a 1-to-2 ratio, but somehow you're going to have to continue to remember the mole ratio tells you how many molecules there are. All right, let's jump into this now mathematically. Let's break this up into pieces. Let's figure out how to convert grams to moles for this weird compound, FeTiO3. So I'm going to go and get the weights off the periodic table. Iron weighs about 56. Titanium weighs about 48, and so do 3 oxygens. They each weigh 16. That's a total of 48. So I'm going to add all this together, 56 plus 48 plus 48, and I get 152 grams. Now, that's not my answer. I've got to remember the mole map says to convert grams to moles, I need to divide. Here's where it gets tricky, and you got to remember this. You will start off on the wrong foot. Always write down what you are given first. Write down your starting amount, divide by what you looked up. Now we have a path to get ourselves to turned into moles. So 46.5 divided by 152, and I get 0.306 moles. All right. That's how we convert grams to moles. Well, now, coincidentally, not really, what if I have 0.306 moles of that same material and I want to convert it into CO2? The ratio between those two materials is 1 to 3. Now you say to yourself, well, which one's the 1? Which one's the 3? It's always in the order in which they are written, is following the way that they are presented to you in the problem. There's supposed to be logic between this. They wouldn't mix those up to try and confuse you and make you guess. It's not how it works. So if I have 0.306 moles of the FeTiO3, and the ratio is 1 mole of FeTiO3 for every 3 moles of CO, I now can find out how many moles of CO I've produced, and it's 0.198 moles of CO. All right, well, let's now take the next step. What if I have, coincidentally, 0.919 moles of CO, and I want to convert this into grams? So what do? Well, I go and I look up their weights on the periodic table, and I remember that to convert moles into grams, I need to multiply. So I'm going to multiply by the weight added up of this C plus O, which is going to be 28 grams for every 1 mole of CO. Those units are going to cancel out, and I got my value times 28, and I end up with somewhere in the neighborhood of 25.7 grams of CO. Step by step, you just solved a 3-step stoichiometry problem. You just went from the far left side of the mole map on the double mole map into the right side of your mole map. So what you did on this mole map is you converted the starting amount of FeTiO3, you turned it into moles. This was step 1. Then we said that there was a 1 to 3 ratio. So we converted this into CO, moles of CO. And then I multiplied by the weight to turn this into the 25.7 grams of CO, my final answer. This is how we are going to go through this process, is 3 separate problems, but it won't make sense for us to do this stepwise. We're going to combine it all together. And here it is. Here is how you can combine all 3 of those steps into one. Notice what I did. I have a starting amount, 46.5. I divide it by its weight. The ratio then comes into play on the next problem, a 3-to-1 ratio. And then you multiply by the weight off the periodic table. So there are 3 problems here. Now, why are these values canceled out? Well, it's just the units that are canceled out, not the values. Notice they're the same down here, so they canceled out. Notice these are the same, so they canceled out. And then these are the same, so they canceled out. Left with only 1 unit, which is the one you desire. The question was, how many grams of CO are produced? You multiply all the numbers across the top, you divide by all the numbers across the bottom. Now, this works for some people. They're like, this is logical. I get it. I'm down with it. I understand it. show me the first practice problem. Let's jump in. Some of you may still be struggling and say, I'm not quite sure I get this. Let me show you an alternative path to this information. Let's set up ratios. Some of you may say, I love me some cross multiplication. What I'm going to do is I'm going to take into this ratio that I've set up, and I'm going to rewrite it down here. 46.5 divided by 1 times the weight of that compound. I'm going to substitute in for FeTiO3. I'm going to substitute in its weight, 151.73. On the right side, I've got X over 3 times. I'm going to substitute in the weight for CO, 28.01. Now this is a cross multiplication. So I would take 46.5 multiplied by 3 multiplied by 28.01 equals 1 times 151.73 times X. How do I solve for that X? Well, what I'll do is I will simply divide both sides by X. I'm sorry, divide both sides by 151.73. 151.73. That's going to cancel. And what you'd be left with is your X value. And magically, you're going to get the exact same answer if we do the math. Okay. So let us practice some problems now. Here's where it gets challenging right away. You notice I didn't give you a balanced reaction. We have to come up with that. So I'm throwing you. So let's try this. I've got iron 2 sulfide. That Roman numeral 2 means its charge is 2. Now, because sulfur has a charge of -2, this is balanced out. I don't need to do anything. It asks us then, well, how much iron 3 oxide? Well, that's not balanced, so I'm going to crisscross the charges to make it balanced. Well, something happened here. How does S become O? It doesn't change. There's something left out of here. What did I leave off? I left off the oxygen, the O2. Over here, I left off the sulfur. Now, here's the thing that you will not know. Sulfur by itself is always found as an 8. It's octahedral. It's octatomic. Sorry, it's octatomic. So when it's found by itself, it's found as 8. It's weird. Now we got to balance this. So here we go. Let's balance it. So I've got a 2 and I've got a 3. I'm going to flip those numbers. So I'm going to put a 3 here. I'm going to put a 2 here. Now I probably honestly should have started with my, let me start over. I'm going to start with my sulfurs because I see that's going to become an issue. I have 8 sulfurs. I'm going to start there. Now I can put in my 4 for my irons to balance those. That gave me 12 oxygens. That means I need a 6 here. Now it is balanced. Okay, now that we have a balanced reaction, I've got 167 of the first material right here. I don't know how much of this I'm going to produce. So I'm going to take 167 grams of FeS. And I'm going to go and now figure out how much does it weigh on the periodic table. So Fe weighs roughly 56, sulfur weighs roughly 32, that is 88 grams. So for 88 grams of FeS, I have 1 mole of FeS. Now let's take a look at the ratio through the mole map. The ratio is for every 8 moles of FeS, I have 4 moles of Fe2O3. Then the final step in the mole map is to convert moles to grams. So for every 1 mole of Fe2O3, I'm going to add up the weight of Fe2O3, and that comes out to be 160 grams for Fe2O3. So now I'm going to multiply all the numbers across top, 167 times 4 times 160 divided by 88 divided by 8, and I get 151.8 grams of Fe2O3. Okay, let's now do the ratio version of this. So I already previously set it up. Let's reestablish that. So I've got 167 over 8 times FES equals X over 4 times FE203. I'm going to substitute in, because in this substitution, I already now know my weights. This is 88 and this is 160. Now I just cross multiply. So I have 167 times 4 times 160 equals 8 times 88 times X. Divide both sides by 8 times 88. And magically, you're going to end up with your X is 151.8. So you could do this both ways and you can solve this. I believe I have a couple more examples that I want, but I'm probably going to start a different path. I'm going to jump down to number 12. On number 12, I'm going to show you the balanced reaction so we don't get bogged down with this one. So it's got pentane, which is C5H12. It's going to use oxygen. It's going to produce water and carbon dioxide. So we need to first balance this. So I'll put a 5 here. I will put a 6 here. And that gives me 6 plus 10 is 16. So I've got an 8 there. Now it's everything balanced. Okay. What I want you to notice is for the pentane, it's in liters. Now the water is still in grams. That's okay. So we need to go back and look at our mole map for what happens in stoichiometry if I don't use grams. What do you use as your conversion principle? Well, here we are in this problem with the pentane. I need to convert to moles first. And the way to do that is through 22.4. I'll then use the mole ratio and then I will convert it into grams. So I can still use this mole map. I don't have to exclusively always use weights. You can use Avogadro's number, you can use 22.4. And in this particular problem, we are going to be using 22.4 as our conversion. So here we go. I'm starting with 46 liters of C5H12. I'm going to do my railroad tracks. And I know that for every 22.4 liters of C5H12, there is 1 mole of C5H12. That's coming off the mole map. Now my ratio, it is 1 mole of C5H12 is equal to 6 moles of H2O. That comes from the balanced chemical reaction. And then off the periodic table, for every 1 mole of H2O, there are 18 grams of H2O. Where did I get that? H weighs 1. So there are 2 of those H's, and oxygen weighs 16. You sum those together, you get 18. So all I got to do now is multiply the values across top, 46 times 6 times 18 divided by 22.4, and you end up with 220.7 grams of water. Now let's do this as a ratio. So I would have 46 over 1 times 22.4 equals X over 6 times 18. Cross multiply, you'd have 46 times 6 times 18 equal to 1 times 22.4 times X. Divide both sides by 22.4. Cancel out. And you're going to magically get the exact same answer, 221.7. All right. This is everything that I want to share with you. It clearly needs more practice. You cannot feel confident after me working 2 or 3 problems. You need to do some practice problems. So thank you very much. Go and start practicing. I will talk with you again soon. We will practice again soon. Bye-bye.